Before we go into the next example, let's sort of generalize what we just did in the last two examples. All right. In both of those examples, we were trying to figure out the probability of one event given that another event had happened or that it was true. Okay. So we put it in a Venn diagram, but because of the fact that we were given that A was true, one event was true, we had to restrict our sample space, if you recall. We restricted our sample space just down to the one event that we were given was true, right? So, and a portion of the elements in that event were the event that included elements that where B had happened, right? Where B was true. Okay, so in order to calculate that probability, the probability of event B, given that event A is true, is we took the number of elements in the intersection, right? The number of elements where both A and B are true, and divided by the number of elements in A, right? Because we were restricting our sample space down to just those elements in A, because we were told that A has occurred or that A is true. Okay, so we have this result right here that we were using in the last two examples, essentially, just by reasoning it out, right? We want the ratio of the number of elements that are in both A and B, and we need to divide that by the number of elements in A because we were given that A has happened. All right, so we can actually rewrite that in terms of probability. Now, we were writing this in terms of the number of elements in a set, but we can also write it in terms of probability. All right, if I just divide the numerator and denominator by the number of elements in the sample space, okay, I'm dividing the numerator and denominator by the same amount, so it's an equivalent fraction. All right, but then this is the probability of A and B happening, right? That is that probability. And this is the probability that A happens. So now we can rewrite that same result in terms of the probabilities of those events, okay? And this is an important result. The probability of B given A is the probability of A and B happening over the probability of A happening. All right, so that's one important result that you need to know, but I think it's fairly straightforward and understandable. The second thing that we can derive from that result is that the probability of A and B happening is the product of the probability of A times the probability of B given A. Okay, now that's just rewriting this. If I multiply both sides of this equation by the probability of A, right, probability of A, multiply both sides by the same thing, right, then essentially probability of A divided by the probability of A, those just cancel out. Okay, so that's where it's coming from. It's just rearranging that equation that we just got. Okay, but these two are important results. All right, these allow us to work with probabilities in a very nice way. We can use this product rule. Okay, and so let me go on to now example 3 to kind of demonstrate how we can use that product rule. All right, so example 3, we have two cards are drawn without replacement from a well-shuffled deck of 52 playing cards. What is the probability that the first card drawn is an ace and the second card drawn is a face card? Okay, so I'm going to define a couple of events, right? I'm going to call event A. So actually I'm going to switch back to green here. Let's let A be the event that the first card is an ace. And we're going to let B be the event that the second card is a face card. And what we want to know is what is the probability of the first card being an ace and the second card being a face card. Okay, so what's the probability of A and B? All right, now we can just use the product rule. We just learned that the probability of A times the probability of A and B happening is equal to the probability of A times the probability of B given A. Okay, and we can reason out what those are. Probability of A happening. So the probability of the first card is an ace. Essentially, you have 4 face cards and out of 52. All right, so there's a 4 out of 52 chance of drawing an ace on the first card. So now the second probability, the probability that the second card is a face card. So let's think about how many face cards there are. There's Jack, Queen, and King of 4 different suits. So that's 12 cards. But now we've already drawn 1 card, right? So we only have 51 cards left. So the probability of drawing a face card on the second draw is 12 out of 51. And if we just multiply those, now I'm just going to write this as a decimal, right? Put this in my calculator, write it as a decimal. So 0.018, right? So about 1.8% chance that you get an ace and then a face card. All right. Now, this product rule actually extends to more than 2 events. Okay, so that's what this is saying. This looks a little cryptic down here. But if you've got 3 events, E, F, and G, then the probability of all of those things happening together, that E and F and G all happened, is just the probability of E times the probability of F given that E has already happened, and then the probability that G happens given that E and F have happened. Okay, so we can extend this product rule to more than 2 events. That's what that is saying right there. All right, well, I will meet you in the next video.